This video is about one special continuous random variable, the normally distributed random variable. We know some continuous random variables, they have very special distributions. They get their own names. When we talk about continuous random variables, sometimes we will use their PDF, the probability density functions, to represent different types of random variables. The probability density function for a given random variable, given continuous real-valued random variable, is a non-negative function f(x) such that the probability of x smaller or equal to small x from the real line can be represented. That value is equal to the value assigned by a Riemann integral concerning the PDF function. So basically, the CDF for a continuous real-valued random variable can be recovered by the PDF. And if we know the CDF, we can also recover the PDF of the associated real-valued random variable, continuous random variable. In this video, we focus on one special distribution, the normal and Gaussian distribution. This is the second video that we are talking about this distribution. So instead of focusing on the PDF function, we are still discussing the distributions concerning the normal distribution, but given we know the moment generating functions also determine distributions, in this video, what we're gonna look at is the moment generating functions of the normal distributed random variable. And we're gonna make use of the moment generating function to study some properties associated with the normally distributed random variable. So first, let's derive the moment generating function of a normally distributed random variable with mean mu and variance sigma square. You can pause the video at this moment and try to figure out how to derive the moment generating function yourself. Well, let's start with the standard normal distribution with mean 0 and variance 1. Then, based on the definition, we know we need to look at the expected value of e to the power tz. According to the law of the unconscious statistician, this expectation value is essentially equal to the Riemann integral from negative infinity over to positive infinity, right, over the whole support of that, e to the power t small z from the real line multiplied by psi z, the PDF function of this z random variable evaluated at small z. Now, how do we calculate this Riemann integral? If we take a close look of these products, we know it can be rewritten as a constant times z to the power 2 over 2 and minus tz times 2. Now let's plus the term which is t to the power 2 and minus t to the power 2. Notice where the Riemann integral is, we are doing this integration with respect to the small z, so t is fixed. Right here we are considering for a given t, arbitrary given t. Therefore, we can rewrite the integrand inside as e to the power z minus t to the power 2 times e to the power t squared over 2, right? This one remains constant. This one is a constant term. This one is also a constant term. We're going to move this outside, the constant outside the integration, and the integral value remains the same. And what's left is this term. If we take a close look of this term, this is the PDF function if a normally distributed random variable with mu with with mean t and variance equals 1, right? This function is suppose we have a random variable z follows this distribution. You can find out the function inside the integration, inside the Riemann integral, is essentially the density function of this random variable y, which follows normal distribution with mean t and variance 1. Then what is the value if I integrate this density function from negative infinity to positive infinity? We know the integration should be equal to 1, right? Integrate up to 1 if we integrate this y over its whole support. In the end, what's left is just a constant in front. And note, this function is finite for any t from the real line. So the MGF, MZ here is well defined, right? It's finite for all the values from the real line. So definitely we can find some arbitrary intervals, for example, here contains 0. And for any t from this open interval containing 0, this one takes finite value. So the MGF function here is well defined. Okay, the next step is we know if we consider this location scale transformation, mu plus sigma times z, this transformed random variable or this function of random variable z follows the distribution, normal distribution with mean mu and variance sigma square. Then it's easy to calculate the moment generating function based on of x based on the moment generating function of z, right, which we have already derived in the first step. The moment generating function of x is e to the power x, which is equal to mu plus sigma z. Note here, if we look at this new random variable, it contains two parts, which is t mu times t sigma z. The t mu here is a constant, right? So the expectation, if we consider expectation, by the linearity of the expectation, we can move this constant outside, and what's left is here. If we take a close look at this value is essentially is equal to the moment generating function of z evaluated at t sigma. Because based on the definition, we know this value is equal to the expected value of t sigma times z. Therefore, the moment generating function of x, given x is a location scale transformation of z, can be rewritten as e to the power t mu multiplied by the mz evaluated at t sigma. Now what's left is simply to plug in the value to the moment generating function of z. This is the final result you have. So the moment generating function of x is an exponential function with argument mu t plus 1 over 2 times multiplied by sigma square t square. Right? This is the moment generating function of x, which follows a general normal distribution. This moment generating function is also well defined since this function is finite, takes finite values for all t from the real line. So the mx, the moment generating function of x, is also well defined. Notice the key step here is to use the moment generating function of a standard normal distribution to calculate the moment generating function of a location scale transformed random variable. And this relation is true for general local scale transformation relation. If we have a random variable x and z follows this relation, then their moment generate then if their MGF function exists, their moment generating functions will also satisfy this relation. Okay. So here it's also easy to say that if the moment generate if the moment generating function of z is well defined, then the moment generating function of the location scale transformation of that new random variable here is also well defined for its moment generating function. And if mx is well defined, then mz is also well defined, right? So the connection here is quite interesting. Next, we're gonna make use of the moment generating function of normal distribution with mu and sigma square variance to deliver some properties concerning normally distributed random variable. The first property is that, well, let's show this function of random variable, which is a summation of xi minus 1 divided by square root n, right? Not divided by n, but square root n. So this is a rescaled sample mean. Normally the sample mean is equal to xi something, xi divided by n, the summation of xi divided by n, but here we're gonna minus 1, which is the expectation of xi here, and multiplied by extra square root n. Okay, so this is not the sample mean, but it's closely related with the sample mean. What is the distribution of this transformation if we have xi follows IID Poisson distribution with arrival rate 1? We're gonna show that when n is large enough, the distribution of this monster here can be nicely approximated by normal distribution, standard normal distribution. You can pause the video at this moment and try to figure out the argument yourself. Here we are going to work with the moment generating function. The first step is always to derive the corresponding MGFs. So here we have Poisson distributed random variable with a variable rate 1, so xi's. We also have the standard normal distribution here. And first, let's derive, and we also have this transformed, well, this function of xi's, right, which is also a random variable. Let's first derive the moment generating function of Poisson distribute. We know the moment generating function of a Poisson distributed random variable with a arrival rate 1 is easy to calculate, which is essentially the expectation of e to the power tx. Now, by the law of the unconscious statistician, you can derive this result. This function, this moment generating function is well defined because this function here certainly takes finite value for any t in, for example, this interval containing value 0. So the moment generating function is well defined. Now next we're gonna work with a summation of xi's, but also then rescaled by shifted by the constant 1 and divided by the square root n. So what is the moment generating function of y here? Here is the result. I write out the relation between y and the moment generating function of xi minus 1, right? So here, the definition of moment generating function of y is e to the power ty, the expected value of that random variable. And we know this is essentially, right? Let's plug in this relation here. So that would be t over square root n times the summation I equals 1 to n xi minus 1, which can be rewritten as product of e to the power t over n times xi minus 1. And because they are independent from each other, here we have IID sequence, right? So each xy, they are independent from each other, and independence means products. Here for independent distributed random variable, IID random variable here we can interchange the order of expectation and the products, which is equal to the product from I equal to 1 to n, the expected value of e to the power t over square root n times xi minus 1. Right, if we look at this term, this is essentially, if we regard xi minus 1 as a random variable, then this is the moment generating function of xi minus 1 evaluated under the value t divided by square root n. Right, this is the function here. And we're gonna multiply all such moment generating functions together from I equal to 1 to n. Now, what is this value? This is a xi minus 1 is a location scale transformation of xi. Right? For general, if we recall what we have for location scale transformation, the formula for that, if we have mu plus sigma z t, that is essentially equal to e to the power mu t multiplied by the moment generating function of z evaluated at t sigma. Now here, apparently, xi times 1 plus minus 1 here. So we're gonna plug in the minus 1 here, that is, and times the t here, but the t here is t over square root n, so this gives this term. And sigma equals 1 here, right? So this is t over square root n. And we have identical distribution, so each of these moment generating functions will be identical of this format. We have IID sequence, right? Independent and identical distribution. Here, there are n of them multiplied together, so to the power n. Now let's plug in the formula we have derived in the first step. Because x1, it also follows Poisson distribution with arrival rate 1. Now let's plug in the moment generating function we have derived from the first step, evaluated at the value t over square root n, then multiplied by this e to the power minus t over square root n, and altogether to the power n. This is the final result we have. Look at this formula. It's well defined for any t from R, from the real line. So the moment generating function of y here is also well defined. Now we have the moment generating function of this monster. How do we work with this formula? We're gonna apply the Taylor expansion to see what happens when n is larger and larger. But before we do that, let's first take a look at the moment generating function of a normally distributed random variable, which we have already derived in the previous slides, which is in this format, right? E to the power mu t plus sigma squared t squared over 2. This one is also well defined, as we have already discussed in previous slides. Now we're gonna work on the relation between these two functions in color red. So what are their connections when n is large enough? Surprisingly, they again coincide in the limit. Now we're gonna apply the Taylor expansion of e to the power t over square root n, which is the summation of t over square root n to the power I divided by I factorial from 0 to infinity. It's very easy to memorize this relation once you notice the summation of the PMF function of a Poisson distribution with arrival rate lambda need to be equal to 1. You can easily memorize this formula. So we know this is the summation of the PMF function of the Poisson distributed random variable with arrival rate lambda. Now this is a constant. So let's multiply by e to the power lambda on both sides. Right, from this PMF function of the Poisson distribution, it's easy to remember this Taylor expansion of the exponential distribution, exponential function. Okay, now we move on to this step. If we expand the summation here, it will be equal to 1 plus t over square root n plus t squared divided by 2n and plus some terms that is way smaller than 1 over n, right? So here I use a small o and 1 over n to denote all those terms, because all the remaining terms, if you see that the power in the denominator here will be n to the power 3 over 2 and 2, they have all powers larger than 1. And now this is the summation here. We're gonna minus 1 minus t over square root n. That's the first two terms, they disappear, right? What's left is remaining term here. So the function in the middle, that is essentially equal to n times this remaining. This is the power of n. Note here n times this remaining term, and all those terms are of much higher order than 1 over n. So if n is larger and larger, right, n times this small remaining terms, they goes to 0. For example, n times what stays the following terms? The following term will be t over 3 divided by square root n to the power 3 and 3 factorial, right? If n times this one, what's left is t over 3 for given t divided by square root n. So when n is larger and larger, it goes to 0. So n times this small term here disappears when n is large enough. And n cancels each other for the first term. So in the limit, what's left here is e to the power square t over 2. What is this limit? That is essentially the limit, well, that is essentially the moment generating function of a standard normally distributed random variable n01, right? Mu equals to 0, sigma square equals 1. Therefore, we show that the moment generating functions of this rescued or standardized sample mean and the standard normal distribution are exactly the same in the limit. Because we know if moment generating functions exist, they determine distributions. Right here we have same distributions in the limit, which implies in the limit these two distributions, the distribution of this monster and the distribution, standard normal distribution, they coincide with each other. This is a very nice property concerning the Gaussian distribution. Actually, this property holds true for a much larger class of xi's, not only for this Poisson distributed random variable, but there is a general class of xi's such that xi minus its mu, this reskewed sample mean in the limit will follow the Gaussian distribution or the normal distribution. But we are not discuss its details. Okay, so in general, you can find many distributions distributed xi such that xi it follows IID distributions from those distributions, the reskewed sample mean x shifted by the mu divided by square root n and its standard deviation in the end will follow a standard normal distribution. So here we only discuss a very special case here. And the last property we're gonna discuss using the moment generating function is to show that a sum of n independent normal distribution is still normal, right? Previously we have this property is actually also true for Poisson distribution. If we have a sum of n independent Poisson, it also follows Poisson. And here we want to show that a sum of n independent normal distributed random variable still follows normal distribution. And when we have a summation of independent random variables, it's always easier to work with moment generating function. You can pause the video at this moment and try to figure out the step yourself. Let's first derive the moment generating function of x. Let's first write it down. This one has already been derived from previous exercises in this video. And next, we're gonna derive the moment generating function of the summation. And because here we are sum independent random variables together, so the moment generating function of this summation, this new random variable here, the summation of xi, is essentially equal to the product of moment generating functions of each term in this summation. Right? Independence means products. And here we only need to plug in the mu I and the sigma I for each term. So this is the product of the exponential function with argument mu I t plus sigma I squared t squared over 2. And after simple algebra, it can be rewritten in this format. Now if we take a close look at this moment generating function, of course it's also well defined because it takes finite value, for example, for t from -1 and 1. So the moment generating function of this summation is well defined. And this is also the moment generating function of a normal distribution with the average with the mean equal to the summation of mu i's and the variance equal to the summation of sigma square i's. Therefore, because moment generating functions, if they exist, they determine distributions. Right here we have the same moment generating functions. The moment generating functions of summation here is exactly the moment generating function of this normal distribution. So we know a sum of n independent normally distributed random variable is still normal distribution. So in this video, we use moment generating functions to introduce some properties concerning normally distributed random variable or Gaussian distributed random variable. And thank you for watching this video.